In this video, I'm going to talk about the test for convergence called the ratio test. So what the ratio test looks at is looking at the nth term here, and you're going to look at the limit as k goes to infinity of the ratio, thus ratio test, of the nth plus 1 term or kth plus 1 term over the kth term. We're going to set that equal to some value, whatever that value is. If the value is less than 1, the series converges. If it is greater than 1, it diverges, and if it equals 1, the test fails. It's important to note that you can only use this if you have positive terms. If you don't have positive terms, then this version of the ratio test doesn't work. It works really well with products, powers, so exponential functions, and factorials are very common in these. So let's look at some examples. Okay, so in this problem, we have an exponential function and we have a factorial, which is really going to lend itself to our ratio test. So this is going to be my nth term. My an plus 1 term is going to be, we're going to add 1 to that n, and I'm going to add 1 to that n. Then we're going to do our ratio. So I'm going to have the limit as n goes to infinity of the nth plus 1 term always goes on the top. Then we have our nth term. Okay, this is a pretty wild limit. Okay, so we're going to do some algebra to simplify it first. Okay, so I'm going to look at this one. This 2 to the n plus 1, I'm going to rewrite as 2 to the n times 2. Factorials. Factorials are the number times the number 1 less than it times the number 1 less than it, and so on. So in this case, I'm going to take out the n plus 1 and multiply that by n factorial. Okay, that's a way to simplify that. And I'm going to multiply by the reciprocal. Okay, so you can probably see why exponentials and factorials work really well with this test. The 2 to the n's are going to cancel, and the n factorials are going to cancel. So all that's left in the numerator is 2. All that's left in the denominator is n plus 1. And suddenly we have a very easy limit to evaluate. As n goes to infinity, this denominator is going to grow, so it goes to 0. What we care about with the ratio test is that value is less than 1, which means the series converges. So in this one, my an plus 1, I'm going to add 1 to all of my n's. So I'm going to have n plus 1 to the n plus 1 over n plus 1 factorial. Then we'll go ahead and put that in my ratio. So I'm going to have n plus 1 to the n plus 1 over n plus 1 factorial over n to the n over n factorial. All right. Start reducing, simplifying, canceling. Because of how this works, you're going to have kind of matching pieces that'll end up canceling, hopefully. I'm going to rewrite my n plus 1 to the n plus 1 as n plus 1 to the n times n plus 1. I'm going to rewrite my n plus 1 factorial as n plus 1 times n factorial. And then we'll multiply by the reciprocal. So some stuff cancels. My n factorials cancel, and this n plus 1 cancels. So I have n plus 1 to the n over n to the n. Okay, that's still kind of tricky and maybe not totally recognizable. So let's use some properties of exponents. If we have something to the same power, I can go ahead and combine those, n plus 1 over n raised to the n. Okay, still, what is that? This is actually a limit that we've seen before. N over n is 1. 1 over n is 1 over n to the n. If we have 1 plus 1 over n to the n, this is a very specific limit. This gives us a value of e. E is about 2.718, which is greater than 1. So this series diverges. So you might want to try this next example on your own, see what you come up with. I'm going to go ahead and just jump to the limit. So I'm going to have n plus 1 over 2 to the n over n, plus 1, 2 to the n. So I have n plus 1. In the denominator, I'm going to rewrite that as 2 to the n times 2. And multiply by the reciprocal. Only thing that cancels is the 2 to the n's, but that's okay, because it gives me something we know how to take the limit of. N plus 1 on the top, 2n on the bottom. Same degree on the top and the bottom, so this limit goes to 1/2, which is less than 1, so this series converges. Next one. We're going to have 1 over 2 to the k plus 1 minus 1. So I just add 1 directly to that k value. Okay, here I'm going to distribute. I get 2k plus 2 minus 1, which is 2k plus 1. Okay. Okay, so we get that. Degree is the same on the bottom, so we get 1, which is inconclusive, which means we need to do a different test. We will learn about the comparison test is really how we'd handle that one, because it's closely related to the harmonic series. But if you get 1 from the ratio test, it is inconclusive. All right, then we have our classic series multiple choice, where we're presented with several series. This time we are looking for which one of these converge. So let's kind of look at each of these. This first one, 1 minus 5 to the fourths, is just negative 1/4. Okay, which is an infinite geometric series. So they'll often combine different tests that were required in these problems. So it's an infinite geometric series. The common ratio is negative 1/4, so this one converges. This one we did previously in the notes and found that it diverged. We would use the ratio test. Your clue would be when we have factorials and exponentials. Last one, okay, we did this limit earlier. If I look at the limit of my nth term, we get e. And in order for a series to converge, the limit of the nth term must equal 0. This is the divergence test. If it does not equal 0, then the series must diverge. Okay, so the only one that converges is our good old geometric series. So that is the ratio test. We'll be doing a lot more with the ratio test later on.